of Information Systems and Management. So he designs analytics-driven algorithms to solve business problems. So this is something that you will learn today during his lecture. And he often works with industry partners around Tampa Bay and around the US, I guess, and around the world on applied research. And he worked with more than 20 firms on various machine learning and analytics initiatives, and often focuses on innovative applications to drive business value. Now, his research has been published in so many journals that I'll need the whole hour to tell you about them. However, you should know that those are the premier computer science and business journals, and also conferences, okay? So now, with no further ado, Professor Padmanabhan takes on the stage. And again, stay around, cool giveaways all the way at the end of the lecture, and sign up for the lecture that's coming up in 2 weeks.
Thank you, Anna. Thank you so much, Tom, as well for helping organize this session. And thanks to all the participants for taking time off in your day to sign up for this and be part of this. Now, I'm not sure if we can do a show of hands, but maybe if you can just indicate in the chat, for instance, how many of you attended the previous talk by Professor Varol. That would be nice and interesting. He's a colleague of mine and teaches in the same program as well. So maybe show of hands, yeah, just so that I know if some of you have that context or background. Awesome. So it is the number is growing the longer I wait. So so it's a good group. So I think we have about 45 people, and so far about 8 or 9 have attended the previous session. At least it looks like that. This is awesome, and thanks for that interest, because the sessions are quite complementary, but at the same time we try to make each session self-contained. Here. So let me actually share my screen. And so today we have about an hour. And, I think in terms of questions or comments, we'll try and have time at the end. Tom, any specific time you want me to try to finish this by, so that we can have time to discussion? Any recommendations?
I think we're all finished about 45 minutes, quarter of, and then we had questions, and
Okay, something similar. All right, yeah. So I'll try and do that. So hopefully you all can see my screen, and so this is a talk that broadly I think is part of a course that I teach called Data Science Programming. This is part of the curriculum for the online global MS in Business Analytics and Information Systems program at USF, and also part of the weekend executive program in MS in Business Analytics and Information Systems, also at USF. And both these programs are geared towards many times working professionals who need that flexibility to attend these programs at different times and in the weekend. So towards the end, I think Tom will be around to also answer some broader questions about the program itself. But it's in the talk, what I want to do is spend maybe, I have probably more material than I may end up covering. And I don't like to rush. So I may skip a few things here based on how we do on time. But I just wanted to give you a little bit of history of the kinds of problems and work that's been going on in the space, as well as spend the talk talking about machine learning and AI, and some important issues related to these areas that I think a lot of the business leaders and analytics professionals need to know of. So now, if you look at what is called data science today. In one sense, a lot of people look at data science as the intersection of ideas in machine learning and business problems or domain sciences. But if you look at the kinds of work that has gone that has been in this area for many years, I did my PhD in '98 in machine learning. At that point, it was algorithms for pattern discovery. And so I've been working in this area for a little over 20 years now. And early on in the 90s, there was a lot of interest in algorithms for discovering patterns in data. And so a lot of marketing applications of business of algorithms for mining patterns primarily. Then in the next probably 10 years, there was a shift towards predictive modeling. And many of the algorithms were focusing on how do you build large-scale predictive models and generate business value from there. Late 2000s, the shift in this field was towards large-scale experimentation, A/B testing. So not just using your data to build models, but to actually run large-scale tests so that you can very quickly determine if something works or not. And closer to 2010, there was a focus on new data types and novel applications. So a lot of focus on images, video, audio, and the kind of algorithms that are needed to deal with those types of data, as well as new applications that previously people never even thought of as necessarily data science applications. And currently, I think what we are seeing is a very productive and efficient area of data-driven design, where the thinking is not just machine learning or AI for the sake of machine learning or AI, but how do you build effective end-to-end systems that add value? Now, it doesn't have to be business value. It could be healthcare. It could be patient outcomes. But it could be business value as well. And how do you build these end-to-end systems where machine learning and AI are components, but the focus is on delivering value, right? And so it's an interesting evolution. And if you focus on just the machine learning term here, and we'll spend about roughly half our time on talking about what machine learning is itself. If you focus on the machine learning term, machine learning grew out originally of the computer science discipline, and it is a subset of a much broader area called artificial intelligence or AI, which we'll talk about in the second half. But the focus in machine learning originally was on learning from data. So if you had data, can you draw generalizations from it? Now, this is not the only perspective. Subsequently, today, I'll introduce a different perspective of machine learning that will point to some of the newer applications we are seeing today. But if you stay with the data perspective in machine learning, can we build predictive models given big data? This has been an interesting question and lots of work done in the last 2 decades. Now, when you build these types of machine learning models from data, like you get a lot of data, point these algorithms, and press go, and of course it's not as easy as that. But eventually, the models that you build may look like what you're seeing here, right? So this is an example of, in the machine learning literature, what are called decision tree algorithms that you may have seen in Varol's session as well, right? So this is a model where you're trying to take a large amount of customer data and build a predictive model that predicts risk as a function of a lot of customer demographics. And the end result, the model you build might look like this, right? Which says that, if the occupation is a small business owner and income is less than 50,000, credit risk is high. If the occupation is a small business owner and income is greater than 50,000, credit risk is low. Any other occupation, credit risk is also low, right? So this is what the model is predicting, and this is what the model looks like. This is a decision tree model. Now, do all models look that way? No. We have a lot of different types of models that you can build. Today, one of the most exciting areas within machine learning is an area called deep learning, where the goal is to build machine learning models using large neural networks. So a neural network model looks like this, where you have a whole bunch of neurons or artificial neurons and connections between them. And you have inputs coming in the form of raw data, and the inputs get multiplied by each of these connections has a weight associated with it, a weight in the sense a number, a numeric value. And each of these circles, which is an artificial neuron, takes a weighted sum of inputs, applies some kind of transfer function or activation function to generate an output. So the transfer function is a formula, right? So you take a weighted sum of values that come into the neuron, and the transfer function could be something like 1 divided by 1 plus e to the power of minus x, which is called a sigmoid transfer function. And effectively, what that does is it takes all the inputs coming in and it generates an S-shaped output between 0 and 1. Now, each of these neurons behaves that way. And you have this large scale sequential model. And finally, the model predicts some output. And the output might be the object that's there in the image. Right now, the input is, in this particular case, could be pixel values that come from an image. But these types of models can also take as inputs traditional customer demographics. Right? So you can give occupation type, income, and other demographics down here as inputs to the neural network. And you can build a predictive model which is predicting risk, right? Same as here. The two models look very different. One is a tree, a decision tree. One is a large artificial neural network. What is the difference between these two, right? So we'll talk about these things very shortly. So if machine learning techniques can build predictive models that look very different, and and there are many more models than just the two that I showed you, I wanted to spend some time going over some interesting basic concepts in machine learning that are, I find them interesting to think about. But more than that, I think it gives you a good way of looking at what we have in front of us today. So the first question is, if you go back to these two examples and say, well, machine learning models, there are lots of models. You have decision tree models, you have neural net models, there are logistic regressions, there are naive Bayes models, there are support vector machines, there are nearest neighbor models, and there are lots of Bayesian network models, and many of these. And in fact, within the neural network world itself, you have many types of neural networks that you can build. There are ensemble models, random forests, XGBoost, gradient boosted machines, all kinds of models, right? And they all look different, right? Here, one model looks like a tree. Here, one model looks like a network. Some other model may look like an equation. And going back to what we had here, right? So one very basic question that I ask people to think about is, if machine learning is able to learn all these different types of models, why do we need so many types of models? Why not just say, what, tell me the best, right? I'll go and apply the best. I don't want to spend my time learning 500 models or whatever the number is. The answer is, unfortunately or fortunately, that it isn't as simple. Like, all these models are different, and the fact that they're different is what makes them interesting. At the root of what we are dealing with here is just a way of thinking, right? So when you're doing machine learning, the idea is that you have a lot of data and you're trying to build a model, right? Now, another way of looking at what's going on is that the data that we are using to build a model, the data doesn't exist in a vacuum. The data came from somewhere, right? There's some process that constructed the data. And by building the predictive model, what we are effectively trying to do in many cases is to discover that process, right? It's almost like a reverse engineering exercise to say that, look, I know that there was some interesting and complicated process that generated the data, but I don't know what it is. I only had the data. Now I need to learn that process, right? I need to use these algorithms to learn a predictive model that is reflective of the underlying process that's actually generating the data. So this is what we call as data generating processes, right? So another way of thinking about data generating processes, quote unquote, God, right? That's what I tell my students behind the scene, right? So there's someone who's generating all of this thing, and we only see and that person may be using a machine learning model for all you know, right, to generate the data, but we don't know what it is. We only observe the data and we have to infer the process. So in this perspective, when you step back and look at all the different models that we have access to, any of these models is plausible, right? It's quite possible that the underlying data generating process was generated in a manner which was consistent with the decision tree. It's equally possible, not, I don't want to say equally, but it's also possible that the underlying data generating process is resembled how a neural network generates data, right? And that may vary from application to application. And so, given that we have a large number of possible applications in the business world, we don't know the data generating processes. And so having access to the different algorithms really helps here, because by applying the different algorithms, we may then find out how accurate they are on a data set. And if some of these models are more accurate than the others, we may go back and say, you know what, these two models may be more reflective of the underlying phenomenon. And that is why they have higher accuracies than the other models. Right? But this way of thinking, I think, helps you take a much more holistic view of what machine learning models are. So I think, unfortunately, somebody
Balaji, you're muted.
Sorry. Yeah. Can you hear me now?
Yes.
Yeah. Well, how long was I muted?
Just a few seconds.
Okay, good. I don't want to start all over again, but no, I was just saying that there was some background noise that came, so somebody else may have we probably need to be muted. But so the main point here is that by thinking about data generating processes, I think we understand why we have so many different modeling types, and this is important. Now, the second interesting angle to look at machine learning is this tension between symbolic and connectionist models and the importance of representation. Now, in the machine learning world, there has been, over decades of battle between which of these two perspectives is better. The symbolic perspective is this perspective, right? So where the model, the rules are symbolic in nature. If occupation is this and income is greater than 50, then credit risk equals low. Each of these individual terms can be viewed as a symbol in logical terms. And a lot of these models operate on symbols and combine them to come up with predictions. Neural net models, on the other hand, have neurons and connections between them. So this is a very large, complex model. It's very difficult to interpret what's going on. We just have a trained model that has lots of numbers associated with it. But it's very, like here, for instance, you can tell exactly what's going on. Here, it's almost impossible. Not completely, but almost impossible often to figure out what's going on under the hood. So these types of models are actually called connectionist models, where you have neurons connected with each other, and the goal was to learn weights to predict the output. And so there was a tension between which is better, right? And the answer, of course, is whichever is closer to the data generating process. But given that we don't know the data generating process, in machine learning, do we use symbolic approaches or connectionist approaches? Now, this is where it got kind of interesting in one sense, because the earlier camp, probably for a few decades, the quote unquote winner were these symbolic algorithms that models like decision tree algorithms were very popular in business because they were accurate and they were easy to interpret. And the connectionist models, on the other hand, which were these large scale neural net models, uh, ended up requiring typically a lot more data to train on. And after you train on data, it is accurate, but the interpretability was very difficult, right? So and if you have symbolic models like decision tree algorithms that are almost as good and offer greater interpretability, why would you not prefer that over black box neural network models? And that was the, I guess, point of view that led to very significant popularity in a certain class of models for many years. Last 5 years or so, on the other hand, 5 to 10 years, there's an explosion in connectionist models because the data types that have been coming in have been far more non-standard than just numbers and text. So we have images, audio, video, sensor data, and all kinds of non-standard data types. When your input data is a mix of a lot of non-standard data types, symbolic algorithms didn't do as well. And a lot of the neural net and deep learning algorithms did extremely well in terms of being able to predict. Now, these are not just in the worlds of the Googles and Facebooks. Like the everyday company now has non-standard data. You go to a hospital, a lot of their valuable data now is in the form of images. Now, how do we use it in images to build models, right? And that's where the interest in deep learning and neural net models is, makes a lot of sense today. There are customer service firms where a lot of their data is audio data. You have customers who are, recording. There are phone conversations, and you want to try to build models that predict if somebody is unhappy, happy, angry, sad, so that you can route the calls appropriately. Those types of data, again, are the types that are good for these deep learning and neural net models. So it's important to understand that to see the popularity of these types of models. Now, in machine learning, there's also this focus on evaluation, where we have different data sets, and the focus is on building predictive models that hold on test sets. And the thinking is, there's a training data set, which is a subset, where you can do what you want, right? So you can play around with that, try to build as many models, tune your parameters, do whatever you want. Then you use a validation data set internally as a test set to pick the best model. But then eventually you want to have a separate large holdout testing set where you then test the model. Now, this is important because a lot of the machine learning models come with plenty of complexity that you can literally increase and decrease almost like a sliding bar. Now, with complexity, which we will talk about right next, is an interesting cost. Right? So in machine learning, there's a trade-off called the bias variance trade-off, which captures an interesting concept of as your model that you're trying to learn becomes, has more complexity, what kind of trade-off do we encounter? Now, what we generally find is that when a model is less complex, it gets fooled less by random noise in your training data. It doesn't learn the random noise in the training data. And those types of models actually turn out to be a little more stable in the kinds of predictions they make. Now, if you have a very complex model, those models are also prone to learning more noise that may exist in your training data if you're not careful. And as a result of that, the predictions may also vary a lot. Like if you add noise, the model may be completely different, and it may predict very different things than it did before. At the high level, what this says is that being able to build very complex models is a double-edged sword. It does help you build very good models if the data set requires such complexity, right? So in other words, if the underlying data generating process or God generated a tremendously complex model, then using a tremendously complex model will pay off. But if that doesn't exist, right? If the data generating process is relatively simple, if the underlying real model is relatively simple, but there is a lot of noise in the data that comes from randomness in real life. At that point, if you actually deploy a very complex model that comes with a lot of complexity, bad things can happen. It can learn the noise in the data, and it can actually perform worse than the simpler model. Right. So this is an interesting trade-off to think of in real life, where model complexity can be a good thing and a bad thing. And if you're not careful, it's very easy to quote unquote overfit, which is build a model that appears to work on your training set, but performs miserably when you actually deploy it in practice. So this is why it takes a lot of time and effort to build machine learning models well. And it is not easy. It's not just buying a tool off the shelf, hitting a button and saying I'm done. There are lots of things to think about in terms of ways that can go wrong, as well as things that you can do to increase your chances of building good models. Now, there's a lot of interest in machine learning on what I call these ensemble methods, which are model combinations. And again, this ties nicely with the data generating process, at least ties nicely in my head. And I hope I can convey a little bit of that to you here. It ties nicely with the concept of thinking of data coming from some underlying process. And we as data scientists are trying to reverse engineer or guess that underlying process, right? And the intuition is this, right? So we have some models in our toolkit, decision tree models or neural net models or logistic regression models. The models in our toolkits have representations which we as humans created, right? So one model, the representation is a tree. Another model, the representation is a neural network. Another model, the representation is an equation, right? Now, who created those representations? Humans or data scientists did it, because those are the kinds of things we could think of. Is there any reason to believe that the underlying data generating process in nature has to follow a tree or an equation or a network? The answer is we don't know, right? Nature can be a lot more complex than the types of representations that we as humans have come up with in 20, 30 years. So if the underlying data generating process can be, there is a process, but maybe that process is very complex in real life, and it doesn't neatly fit a tree or a network or a equation, then what do we do? Now, it turns out that by combining methods, if we build what are called ensemble models or mixture models or model combinations, if we combine neural net prediction with the decision trees prediction, with the logistic regressions prediction to get a meta prediction, that kind of a model combination ends up creating newer representations that look different from a tree or a network or a regression. It's trying to combine all of these aspects together to create newer meta representations. And those are that. So if you look at the prediction competitions that exist on some well-known sites like Kaggle, where biz companies put out data sets and data scientists work on prediction competitions, two types of methods have done very well in most of the prediction competitions in terms of the winning methods. One class of methods are the connectionist deep learning methods. Another are ensemble methods, mixture models. And that's good to know. And I think there's some, hopefully if you followed a little bit of what I was trying to say here in terms of how ensemble methods actually generate meta representations, that starts making sense. Why these types of models end up performing better in real life, because real life, the data generating process is perhaps more complex than any of our models that we know or understand, right? So now in practice, machine learning is very interesting because your job never gets boring. It's never a one and done thing. In most interesting real life applications, now people are understanding that the underlying process is also changing. What we think of as the data generating process is not static, right? So if you think of the data generating process as a customer deciding to figure out what restaurant to go to, that choice of a customer deciding what restaurants to go to changes when the underlying environment changes, right? When COVID came, people were not, using the same rules. They started ordering online, and that may have completely shifted the way they think of restaurants, right? That sort of a phenomenon is called concept drift. In a COVID case, it's really a very, very big drift. It's a move towards a new regime altogether. Typically, these drifts are more gradual, right? So consumer tastes change as a result of the external environment. And if you don't understand that, then your machine learning model will break. It was built for a world in which consumers had certain tastes and certain preferences because you had your data, but you're then using it in a world in which things have changed. This happens a lot in fraud detection, where people end up building models to predict fraud based on large historical data, and then magically hope that it will work in the current situation. Fraud detection is probably the scenario where you have the most concept drift, because your thieves that you're trying to catch are likely not using the same underlying rules over time, right? They're constantly evolving themselves to avoid being detected. And so within machine learning now, there's a lot of interest in studying this and how do we deal with retraining our models so that we capture concept drift. Another tension that is coming out a lot is this tension between causality and predictability. There is an understanding, I mean, if you look at statistical models versus machine learning models, a lot of the machine learning models came from a world where the focus was prediction and not causation. And so practitioners sometimes incorrectly combine these two. They end up building a machine learning model, look at the variables that show up, and then in a slide that they use, they start using the variables that come up and start claiming causality, saying age causes default because in my decision tree model, the most important predictor was age. Now, age is predictive of default if it shows up in a decision tree, yes, but to establish causality, there are many reasons why age could be predictive without actually causing it. And one reason is that there is some latent variable behind the scenes that affects both of these things the same way. So this is something we also discuss in great depth. It's a very important issue in machine learning now. To understand the distinction, it's very important in practice. But in machine learning itself now, there are newer methods that are trying to get to causal machine learning. It's much, much harder, but it's an important area to keep an eye on. Now, one of the things we are seeing now in ML is an understanding that you have not just expected consequences or predictions, there are lots of unexpected consequences as well. And fairness and bias are areas where this is being looked at very carefully now. Machine learning systems that select customers to offer loans to or interest rates to and so on, if you're not careful, may end up having very systemic bias built in. And these could cause problems to companies if they don't deal with them correctly. Many years back, you could have said, this is not, I didn't know, right? But today we know that these types of problems can happen. And so if somebody still tends to turn a blind eye, obviously that's not good business practice. And we're seeing more and more firms treat this seriously. So let me just shift to a few different slides here. And so I said, like, there's a different machine learning perspective now than probably before. And they are related, but take this perspective, for instance. So humans learn, and can we learn from how humans learn to better understand how machines learn, right? So in fact, one of the broader definitions of machine learning is exactly based on this. How do you teach algorithms? How do you make algorithms learn by looking at how machines learn, right? And so the learning from data is actually is consistent with this concept, because humans learn from examples, and so can you build algorithms that learn from examples, right? So that's how the previous perspective also fits in. But if you take the perspective of human learning, now there's a lot of interest in a few new machine learning algorithms within deep learning called few-shot learning, zero-shot learning, or transfer learning. So few shot learning, for instance, I mean, the idea is simple. The idea is to say that, look, today, if I have to train a machine learning algorithm to do image classification, and I want it to work well, I have to give it hundreds of thousands of images and train it on a large image data set before it learns whether an image has a Starbucks logo in it or not. Now, humans, on the other hand, don't need so many examples, right? If they see Starbucks once or twice, the third time they see a logo, they know it's Starbucks, right? So how is it that humans only have to see the logo twice, and that's enough for them? They figured out that the next picture I see is a Starbucks logo, but when you need a machine learning algorithm, you can't just give it two images; you have to give it 200,000. So there's some interesting implications of this for newer training algorithms. One of the most exciting algorithms that also come in frameworks when you take this perspective of trying to learn like how humans learn is this whole emerging area called reinforcement learning. In the machine learning field, this is actually an old area, but this has been made prominent by Google's DeepMind unit that built the AlphaGo engine that essentially beat the best Go player in the world through an algorithm called reinforcement learning. And the basic concept here is, can you train an algorithm by not necessarily just data, but by just giving it rewards and penalties, and then have the algorithm learn over time by playing repeatedly how to be a good algorithm, right? So you can think of trading algorithms where a machine learning algorithm keeps making trades, and the reward it gets is either a positive return or a negative return. And by making many such trades, can it then systematically learn how to trade? And the answer is yes. There are hedge funds and others that have built reinforcement learning algorithms to do automated trading. But this is an exciting area, relatively new in the business side, but has massive potential. Now, in one of my papers recently, we presented this framework of deep learning within a broader context. Now, the details of this picture are not important here, right? What I mainly want to point out is that the gray A box here has many components of machine learning, specifically of deep learning. But if you look beyond the gray box, the things that we care about are how the gray box influences the business outcomes and societal outcomes, not just predictions, but outcomes itself. And how the environment outside, which is the people that exist in your organization, the different organizations, the decisions other organizations make, etc., how this whole thing plays a role in success or failure of the machine learning system you deploy. And generally speaking, now we have an understanding that the ML part that we build is actually embedded in a much more complex system that exists around that. And the success or failure of machine learning is rarely just based on predictions, but it's based on the entire systemic view of what happens in the world around us. When I say world, I just mean also your organization, right? How you use the model, what systems is it integrated in, what processes are being changed, how all these decisions are made impact the success or failure of this entire framework. And so there's an increasing realization that we have to take a much broader view when we deploy these types of models in practice. So just a couple of minutes here, and I'll probably in about 5 or 6 minutes go over AI more broadly, right? So and then link the two, and then we can open it up for discussions. So artificial intelligence is a much broader area than machine learning. And a motivation for AI has always been building machines that demonstrate intelligence, right? That's why it's called artificial intelligence. And one of the earliest AI examples, if you go back 30, 40 years, was a chat bot called Eliza that would talk to people. Right. So this system is still there somewhere on the web. So if you Google Eliza, you may find it. It's 3 decades old. And if you essentially talk to it, right, it'll talk back to you. Right? And this was 3 decades ago, right? So if you say, my brother is sick, Eliza will say, I'm sorry to hear, who else in your family is sick? Now, if you fast forward 30 years, this is what most of us are doing at home, right? So sometime back, I had to make a reservation at a restaurant. This was actually, this particular picture was pre-COVID, my reservation here. So I, called Google Assistant, and I actually tried to make a reservation through Google, and Google Assistant did it for me. And it actually called the restaurant, gave my information, made the reservation, and was interesting, right? So the restaurant owner spoke to the chatbot and took all my details here. So now another example of AI from 30 years ago or so is this example called Mycin, which is again, we're looking at systems that demonstrate intelligence, right? So this system was a rule-based system that would do medical diagnosis, right? So if you put in a patient's conditions and symptoms, this AI system called Mycin would diagnose what disease or condition the patient has. Now, Mycin was built using rules that look like this, and the system itself had thousands and thousands of these types of rules. And these rules essentially were harvested from medical textbooks and knowledge, right? Human knowledge. But if you step back a little bit and say, what is the system doing? You provide symptoms and it does diagnosis for you, right? But inside the system, you have thousands of rules that were put in by programmers. A few years back, this was exactly what AI is doing. So AI was doing medical diagnosis of cancer images, and there was a high-profile competition where they had human doctors diagnose images to predict cancer, and had the machine learning algorithm also do it. And the deep learning algorithm beat the human doctors both in accuracy as well as speed, which was quite interesting to see. Now, if you look at these two use cases, the chatbots as well as medical diagnosis, you might think, you know what, in 30 years, AI hasn't moved too far, right? We were chatting then, we are chatting now, we were doing medical diagnosis then, we're doing medical diagnosis now. Now, the use cases may look eerily similar. And the reason they look similar is that these are great use cases to try and demonstrate intelligence. But when you look under the hood, the difference is, night and day. Right. So this is like, an electric car versus an internal combustion engine. And so the early AI systems that were demonstrating intelligence, they were doing so by pre-programmed logic. We had humans who were actually putting a lot of the logic that made them intelligent. The newer AI systems are learning from continuous data that we're providing it. Right. And so the second approach actually can scale much better, right? So we don't need to tell it knowledge. We just keep feeding it data, and the system then learns using these deep learning models. So today, AI is a mix of hardware, machine learning, visual perception, and speech and language understanding. And there are lots of use cases that appear like magic, where you have self-driving, making appointments in hair salon or restaurants, diagnosing diseases from images, better than doctors, chatbots, and conversational AI. But a lot of AI is intelligent engineering. Like, the core components are hardware, robotics, and data and machine learning. And data and machine learning is used to also do visual perception, meaning the ability to recognize images, as well as speech and language understanding, which Alexa, Google Home, and others, Siri, and so on, provide, right? But even Alexa, Google Home, Siri, or and the ability to detect images and self-driving, these are also built using data and machine learning. That's why I have a link between these two. But it makes sense to think of these four as components. We have hardware and robotics components, there's data and machine learning, there are visual perception tools that you can literally buy off the shelf from Amazon as APIs. And then there are speech and language understanding tools, again, you can buy off the shelf from third parties. And by combining these pieces together, you can actually design experiences that make it look like magic, right? So if you take self-driving is a mix of hardware and robotics, data and machine learning systems that are able to recognize images. And it, in the future, may also use speech and language understanding, where we can talk to the car, not just have it drive itself. And not just because we don't have a companion in the car, but sometimes it may tell the car, hey, slow down, you're going too fast. Right. Now, you also have other use cases that can tap into some combinations of these things. Chatbots, for instance, can use machine learning and these things. Now, the reason I bring this up is that a lot of use cases in AI that look like magic are actually intelligent engineering. By combining these pieces, you can actually design experiences that demonstrate that demonstrate a lot of intelligence. So if you look at AI today, it does use machine learning and robotics and hardware, but there's a lot of domain knowledge, design thinking, creativity, experimentation, and willingness to fail, because many times we have success stories like the self-driving cars. And many years back, IBM's AI system then was actually benched by the top cancer hospital simply because they didn't think it worked, for their purpose. At least this was 4 years ago. Since then, Watson has, of course, made tremendous improvements, and IBM Health and its use in health has been quite remarkable. But this was what happened 4 or 5 years ago. So there are success stories, there are failures, and often we are biased towards success stories. We hear more successes than failures. So AI is hard to engineer, but if done well, we can get some phenomenal use cases that are awesome to see. There are lots of interesting trends and issues. I'm just not going to go through these things, but in the course we definitely get through a lot more of these things and discuss all of these in our programs here. And then there are interesting questions on futuristic questions in this area that we talk. Now I'll point to a couple of things here, which is this. Maybe if I had to pick one to try and end with, it is this understanding today that we have that machine learning for the sake of machine learning is not helpful. You can be the best data scientist in the world, build the best models, but it can fail in practice. Your company can actually lose money by using it, or nothing may happen, right? And in fact, a lot of companies are struggling with demonstrating return on investment from machine learning for different reasons. And now, one of the things we do understand now is that value is created from systems, not just from predictive models. And so thinking of what we're building from a systemic perspective, therefore, is far more important than thinking of doing it just from a component perspective or just a machine learning model perspective. So there are other things that we can discuss. If we had time, we can go on forever here. But I just wanted to step back a little bit and say, a lot of what we were discussing here, I cover in this course, data science programming down here, which is one of, in our MS and BAIS program, we have probably more. This is an incomplete list, but we have about, in the last many years, we've had students do about 11 courses that are all data courses. And the data courses basically span a statistical perspective, a database perspective, predictive modeling perspective, scalability and infrastructure perspective, and a visualization perspective itself. And this is like, I think the thing that we're working with or dealing with here is like the proverbial elephant, right? So to fully understand it and manage it, it's not enough just to be a blind man who touches parts of the elephant and thinks it's a snake or a pillar. You actually have to be able to touch all the different parts to get the full perspective that what we're working on is an elephant and not a snake. And that's why the different perspectives that we have here and the courses that fall into this perspective, I think adds a lot of value and differentiates this program that we do with a lot of very good programs that are out there. So with that, sorry, I have so many different things here that I'm stopping Zoom instead of Teams. So wanted to leave a few minutes for any questions, comments from the audience on either anything we discussed or the courses in the program, because some of you have a lot of experience working in this area too, I'm told. So would love to hear your thoughts. or questions. Tom, do you want to maybe then?
Yeah, I have a couple slides that I can share, just 2-3 minutes. For those of you obviously are on this call, you have an interest in analytics, in data analytics. If you're thinking about how do I engage, how do I gain those competencies, and acquire the credentials that will accelerate my career, because I know that analytics is sweeping every industry, every functional area on the planet. Then you probably are considering or should consider an advanced degree in data analytics, and that's what we offer to working professionals, and that's the programs that Balaji has been alluding to. So we have a new offering, which is an online version. We had a lot of success in delivering our weekend executive program where folks came to downtown Tampa and attended live, in-person classes. And we found during the pandemic we could deliver, comparable value remotely using MS Teams, just like this session, where you'll learn in a classroom setting just virtually. So that's the difference between our program and other online data analytics programs, is that you'll be, in live lectures interrupting Balaji every 5 minutes saying, I don't understand. Can you explain that another way? So this program, and I'll just share my screen for a minute here. Let me know if you when you can see it.
I can see it.
Okay, so it's structured so you can complete it in 12, 24, 36 months. Our first cohort is going to start January. So you could have your Master of Science in Business Analytics and Information Systems next December. It's STEM designated program, which is important for a lot of folks that maybe don't have a lot of technical credentials. You will when you complete this program. Data, analytics, technology, and management. We're looking to craft professionals that into leaders in data analytics investments at their organizations, and live classes on Saturday and Sunday. All classes are recorded, so you can go back and watch those courses. Core courses are listed here, and the electives that we've chosen. And you can see that statistical data mining is right here in the fall semester. Data science programming is here in the summer. This is what a one-year program would look like. And I sent a link to a brochure in the chat, so you have all of this information. So the program, it's half of what you're going to pay at other institutions. And again, all the instruction is live. So I implore you, if you're going to look at an analytics program, make sure you understand when it says online, if it's live instruction, you're going to be or if you're going to be watching recorded videos. Because again, that is a big difference in a technical program. Is can you actually sit with faculty live and ask questions, interact with your cohort? Everything's included in this. There's no additional fees. Software licenses for classes, so special program only events, networking events. So again, just that's the purpose of these sessions, is to introduce some of you to our program and to share what's taught in this program, because many of you may think, well, data analytics, masters in data analytics, that sounds a little bit intimidating. But folks in our program have come from the business. Probably 40%, Balaji, would you say, come from finance, HR, sales, consulting, and then maybe 60% come from an analytics team already, or IT. We've had from the CTO of Tampa General Hospital down to an analyst, CCG consulting locally. So it really runs the gamut, all looking to accelerate their careers. Many of them are on the call. I'm happy to see many of you dialed in, and I really appreciate that. Still plugged into the university, and many current students are online as well. So with that, I'll leave it to to questions for Balaji, or if you have questions about the program. I know Anna's going to want to give away some of this nice merchandise that we have to a few lucky folks. But first of all, are there any questions about the lecture, about the program?
I'll be here.
Hi, Professor. Can you show us the slide 4 again?
On the mine or Balaji's?
On your screen right now, the
Okay.
4th slide.
The 4th
had
slide.
the subject breakup, the course breakup.
Oh, okay. So obviously, if you split this into 2 years, you would take 1 or 2 classes in the first semester, similar in the second, similar in the third. If you split it into 3 years, you would take 1 class each semester. And I structured the tracks, so the 1-year track, the 2-year track, the 3-year track, so you have the courses that are complementary next to each other. So you wouldn't want to take one R course in the first semester and not take another one for 2 more years. So there's a structure that you'd follow that I would I'd share with you if that's what you chose. This is the 1 year, right? I want to finish next.
Thank you.
Sure.
Yeah, I have a question. So I am I would say a recent graduate from last December from the Entrepreneurship in Applied Technologies program. And I'm definitely an international student, was doing my OPT. And during my work with the software company, that's when I kind of gained interest in data analytics. I was also a graduate assistant, so I was assisting with all the Tableau assignments, and I'm also certified with Tableau and Google Analytics, so that's where it stemmed from. I was actually applying for fall of next year, and I was applying to the data analytics as well as, I believe, the business intelligence. It's one program. How similar or different is this to that?
Balaji, are you familiar with those?
Are they master's programs? These are masters in?
Yeah, masters at USF.
In which again?
It's the business analytics, or no, data analytics and business intelligence. MBA.
Oh, the MBA. Oh, I'm sorry. Yeah. So
Sorry.
the MBA has. So this is an MS, right? And the MBA has tracks in analytics and business intelligence too. And it's interesting because if you look at the MBA's original purpose, typically MBA students do courses in finance, accounting, operations, marketing, management, information systems to get this broad perspective of being in business. And then within the electives, they can do more in one area, right? And that's the purpose of an MBA. And so I don't want to use the word generalist, but historically, a lot of the MBAs have excelled in being generalist because there's a big need for that in the workplace, right? With those types of skills. Now, the MS programs, on the other hand, are trying to be more specialized. And they are trying to build more specialists, but that doesn't mean technical, right? So specialists could be within the analytics role. You can also have a much more managerial focus versus a hands-on focus. And the specialized programs like the MS programs do a great job at preparing you for that range within a specialization. So if you take our MS in Business Analytics and Information Systems program, it's possible to do 9 courses on the data side, right? In a probably 11 or 12 course program, which is a lot, right? So most of the courses you're doing are related to your specialization. But the trade-off is you're not doing courses in finance, accounting, operations, marketing, because that's not the focus of an MS program. That's what the MBA does. So you can, they both take you in different paths. And I think they'll both take you to great destinations. One might take you to Paris, another might take you to London. Right? So, but I think talking to people who've gone through these programs will get you a good sense of maybe which of these two might be better for your own career path.
Do you have any recommendations of who I can speak with?
Oh, I can. There's folks on this call.
Yeah.
If you email me, I'll put my email in the chat. I'll be happy to plug, at least on our end. And I know the director of the MBA program I can hook you up with him, and he can put you in touch with some of their alum as well.
Students, yeah.
Okay, yeah. I did both. I did my undergrad at USF as well in marketing and my master's in entrepreneurship. But I just found that I'm very curious about, especially with the shift last year that happened. I'm just very curious with, about like the data analytics, all of that, and like learning the, like you said, the ML, the Java, all of that. It's very also, how should I say this? The demand is high for it as well. And I'm like, I am very interested, but I was just worried whether I needed some sort of background to actually enroll or to pursue this.
Yeah, so I think one of the things that Tom did mention, which is worth emphasizing here, is that the MS BAIS program, within this, there is a variance. There's a distribution of people. We have some students who are leaning much more heavily on the management side of analytics,
Right.
and others who may lean more heavily towards the implementation, coding, development side of analytics. We have some brilliant programmers who come to this program who will walk out and write, even better Python code than they knew coming in. And then there are others who come in knowing nothing of Python, who learn enough to appreciate it, but they'll shift towards roles in industry that doesn't require them being the programmer, but closer to them being the manager and working in teams. So, Tom, I think a lot of our alum fall into these two categories, right?
Yeah, absolutely. Those are the runs the gamut, the spectrum.
Yeah. So now, but from a student perspective, you're worried. You're saying, if I don't know this, am I going to come in and do badly, right? And the answer to that is usually no. There are many ways you can do badly, but I think you've already proven that you're tremendously intelligent because you've already done degrees from USF, right? I'm not sure the other people in the call can say that. So I don't think you have to worry much, but we do I think in the program, we do boot camps and so on. So I think for students who start in the program here and a lot of the projects are teamwork as well. So as long as you can contribute and bring in your perspective, with the right teams, you can do very good projects. But that said, I think there will be courses where you have to sort of dig in your heels and work on details yourself. And there will be very managerial courses too, where some of the hardcore coders may struggle, right? It may be very new material for them to think qualitatively. So it's an interesting mix.
Yeah. And if you have a business background, I will say that, having come from a business undergrad and then having done a full-time MBA program, I added a Master of Science in Finance because I realized the credentials, it was important for me to have something technical, something quantitative. And that got me my, the great job I had for 8 years out of my MBA program. You want to weigh that as well, everyone's context is different and objectives are different.
And it's not an either or, right? Because you have students who can do an MS in BIS and then an MBA, right? Who, you build the specialization and then, because, you're looking at your career over the next, I think, 20, 30 years, right? 40 years. So there's plenty of time doing the pieces and then start putting it together. Now, the sequence in which you do it, I think could be, now, if you did both, I would do the specialized first and the general later. I think that sequence makes more sense than general first and specialized later, although there will be exceptions to any rule.
Right. No, and I really appreciate that because going through this year of working, I realized that I'm not considered specialized in anything technically with the degrees that I have. That is why I'm okay, I want something more, specialized, technical, hands-on, that I would be considered as a professional in this skill or, a skilled person in this area. So I really appreciate that. One last question, and I swear I'm gone. Are we late for the applications for January or?
No, we'll take applications. I'm going to say December 1st is the date that I've been telling everyone. We're filling up pretty good so far. I'm very pleased, just having only been recruiting for 3-4 weeks for this program at the interest. So yeah, December 1st, you'll be fine. And then always reach out to me if you have any questions about application, the process. And of course, we may end up taking applications, into the middle of December, but this first is our deadline, our first deadline that we have.
And Maria, I think you can also reach out to Jason on the chat because I think he is doing the other route. He has an MBA and he's going into the MS route. So it might be an interesting conversation to have there. But I think Jared had a question.
Hi, I just wanted to say thank you very much for the presentation today. And then as an undergraduate in business analytics right now, I'm graduating next semester. So I'm kind of weighing my options of jumping into the workforce or going for a master's program. In reference to the master's program, do you think it would be better to continue going down the master's route in business analytics again, or would it be better to more differentiate it into another field? So for example, like Thomas, how you did the finance route for your master's program?
I think that it depends what type of competency you've developed. Now, you can get a degree in undergrad and be extremely technical, or you cannot be. And what type of role are you looking for? A business analyst role? Or are you looking to join an analytics team? Those are going to require different levels of competency and different skills. So I'd be happy to talk to you. You can stop by my office anytime, Jared, or give me a call and give you some career guidance. I mean. I've plenty of industry experience here in Tampa overall, before I came to academia. So I'd be happy to, share sort of my opinions with you on what where you should head.
And Jared, I think maybe the way to sort of think through this is to look at it as different options that lead to different destinations, right? Because I think if you think about in your head which is better, then you go in with like some sense that there's a normative answer that one is better than the other. But I think it's more like, they take you in different paths, and no path ever, most of you are at least young enough professionally that you have plenty of pivots that you can make in your career in the next 30, 40 years. So nothing is ever final. It doesn't lock future opportunities, but every path you take does, lead you to different roads. It's like, one exit takes you to the beach, one exit takes you to downtown. Both are good. It's not like New Jersey where all exits take you to a traffic jam. So, but I think, if you think through the different paths in front of you, I think that might help you figure out, which one is better.
Thank you. Love the analogy.
Maria, is that hand up from before, or is that still have a question?
From before.
Okay. I don't know. Do we have any more questions in the chat?
All right. No, I think this is good. And remember, it's November 19th, which is in 2 weeks. We have the lecture on statistical approaches, and that will be on the basics of inferential statistics and R programming. So this is our last lecture for the intro to data analytics. Now with this, I will ask
Anna, just one thing I want to add on to that. That will be more introductory. That is a course covered in our first semester. So it's if you haven't had statistics before, this is a good lecture to listen to, because it's the first one that you would have to reacquaint you with statistics. So I encourage you to log.
All right, this is it. And now we do want to do a little giveaway. So I have from 1 until 98. So Balaji, I will ask you, Professor Padmanabhan, any number 1 to 98.
49.
All right, 49. I have Sanal Prabhuni. If you are still here, please email me directly, and we will send you some nice giveaway prize. Now, one more time, Balaji.
24.
24. Okay, 24 is Matthew Southworth. If you're still here, please send me an email and you're getting a prize. And final number.
83.
83? Oh, 83 will be Raj Makhirji. If you're still here, send me an email. And okay, let's do one more just in case those are not here.
37.
All right, that is 37 is Prahalada Reddy Damata. Send me an email. All right, and we'll get you information. Any questions, every participant should have received my email. So you have the contact information for me. You have the contact information for Tom. So anytime, reach out, okay? And we will see you all in 2 weeks.
And Anna, I just wanted to end with a small personal story that you reminded me of here. 25 years ago, I was, I had randomly parked a car and I had taken my parents somewhere, and I was just waiting outside, with shorts and a t-shirt. And a random person who was, spiritually dressed came up to me and started talking. And so he asked me, can you, think of a number between 1 and 10, exactly like what you said, and and I just wanted to ignore him. I didn't want anything to do with him. So I thought of 5, and then I said, you know what, 5 is like right in the middle. So let me think of 3. And so he responded saying, you thought of 5 and you changed it to 3. And that, blew me out. The conversation got interesting after that. So I don't have time to share that. So most of the numbers, I guess now I started right in the middle and then I kept changing. So I recall that, really strange and interesting conversation from
Interesting.
a long time
Wow.
back.
This is great. Thank you so much. All right, guys, we'll see you all in 2 weeks. And if you're in Tampa, try to stay dry. It's like pouring rain here since the morning. All right, everyone, have a wonderful Friday. Bye-bye.
Thank you very much, Ann.
Thanks.
Thanks, Balaji.
Thank you, Professor.
Thank you.
Thank you all.